In the heart of the Italian peninsula, a small settlement nestled on 7 hills began to stir. Its lifeblood was a single source, the Tiber River. For centuries, this winding waterway provided everything: fresh water for drinking, a highway for trade, and a natural defense against rivals. But as the small settlement swelled, transforming from a town into a republic, and then into the heart of a vast empire, the crisis was brewing. Rome became a megacity, the first in history to house over 1 million souls. The city's colossal growth choked its own lifeline. The same river that had nurtured its birth was now becoming its poison. Imagine the scene: runoff from countless streets, waste from workshops, and the sewage from 1 million inhabitants all poured directly into the Tiber. The once dependable river turned murky, a breeding ground for disease. Sickness became a constant shadow lurking in the city's water supply. Beyond the filth, there was a simple, brutal problem of quantity. The river and the city's shallow wells could no longer satisfy the staggering demand. The thirst of 1 million people, the needs of public baths, and the constant threat of fire required a volume of water the local sources simply could not provide. Roman engineers, the most brilliant of their age, faced an unprecedented challenge. How could they deliver a river of pure, clean water to the heart of the world's most powerful city? The answer was not to be found in Rome itself, but far away in the distant mountains. The solution required ambition, ingenuity, and a mastery of engineering that would echo through millennia. This dire necessity would become the mother of one of history's most iconic inventions. Before great empires could rise, before sprawling cities could thrive, humanity faced a fundamental problem: water. A city needs a constant, reliable source of fresh water to survive, to grow, to flourish. But what if your ideal location for a defensive citadel or a bustling trade hub was miles away from a clean river or a pristine lake? Do you abandon the perfect spot, or do you solve the puzzle? The ancient world's engineers chose to solve it, and their solution was elegant, powerful, and driven by a force as old as the universe itself: gravity. The concept is brilliantly simple. Find a water source, a mountain spring, a clear lake, at a higher elevation than your city. Then build a channel, a conduit, with an incredibly gentle, consistent downward slope. Think of it not as a steep slide, but as a long, slow, patient ramp. Water pulled by gravity would begin its journey. It would flow for miles, crossing valleys and tunneling through hills, all on its own. No pumps, no complex machinery, just the silent, relentless pull of the earth. The engineering was the true marvel. The slope had to be perfect. Too steep, and the water would flow too fast, eroding the channel and causing destructive surges. Too shallow, and the water would stagnate, becoming undrinkable. Surveyors use simple tools like the chorobates and groma to measure these tiny gradients over vast distances, achieving a level of precision that remains astonishing. This mastery over a simple principle allowed civilizations to bring life-giving water to arid plains and bustling urban centers, fundamentally reshaping where and how humanity could live. The true genius of the Roman aqueduct wasn't just its monumental scale, but the invisible, almost imperceptible force that powered it: gravity. Moving millions of gallons of water across vast distances without a single pump required a solution of breathtaking precision. It was a delicate balancing act. If the channel's slope, its gradient, was too steep, the rushing water would act like liquid sandpaper, eroding the stone and mortar, eventually destroying the structure from within. But if the gradient was too shallow, The flow would slow to a crawl, becoming a stagnant, sluggish mess, a breeding ground for algae and disease. The water would never reach its destination. The solution was the perfect gradient, a precise, controlled decline, often just a few meters for every kilometer traveled. Think about that, a drop of only 1 or 2 feet for every 1,000 feet forward. How could they possibly measure something so subtle across rugged terrain? They used sophisticated tools, the king of which was the korobates. This long wooden plank, about 20 feet in length, was their high-tech level. It had a groove carved on top, which they would fill with water. If the water sat perfectly even, the surface was level. On windy days, they relied on plumb lines hanging at each end. By marking a true level, they could then calculate and construct the impossibly slight, life-giving angle needed. It was this mastery over the smallest of angles that allowed them to conquer the greatest of distances, ensuring a constant flow of clean water, the lifeblood of Rome itself. The Roman Empire's ambition wasn't just in conquest, it was carved in stone and water. Aqueducts, the arteries of their civilization, stretched for miles. But what happened when a mountain stood in the way? Romans didn't always go around, they went through. This was engineering on an epic scale, a challenge of precision, brute force, and unwavering confidence. The plan was audacious. 2 teams would start on opposite sides of the mountain and dig until they met in the middle. But how could they ensure a perfect connection buried deep within thousands of tons of rock? The answer began not with a pickaxe, but on the mountain's peak. Surveyors, using tools like the groma, would plot a perfectly straight line over the summit. From this line, they dropped plumb bobs down the slopes to mark the exact start and end points for the tunnel. With the path set, the grueling work began. Men armed with dolabras and chisels hammered away at the rock face day in and day out. For harder stone, they employed a terrifyingly effective technique, fire setting. They would build a massive fire against the rock, heating it to extreme temperatures. Then they would douse it with cold water or vinegar, causing the rock to crack and shatter from thermal shock. As the tunnels crept deeper, fresh air became a vital concern. Vertical shafts were dug from the surface to provide ventilation, a lifeline for the workers below. For months, even years, the 2 teams dug in near total darkness, guided by little more than measurements and the sound of distant hammering. Imagine the tension the final few feet. Was their geometry correct? The breakthrough was a moment of pure triumph. A single pickaxe swing, and light would flood in from the other side, revealing the faces of their colleagues. They had done it. They had conquered the mountain, not by leveling it, but by piercing its heart. A testament to Roman ingenuity, the newly opened tunnel would soon carry life-giving water, proving that for Rome, no obstacle was truly insurmountable. Roman engineers faced an immense, unyielding challenge. How does an empire span the chasms of the earth? How do you conquer vast, deep valleys without modern steel or reinforced concrete? Their answer was not merely a bridge, it was an architectural revolution, a principle of physics captured in stone that would echo through millennia. They perfected the simple yet profoundly brilliant concept of the semicircular arch. Let's build one. Imagine a series of precisely cut, wedge-shaped stones called voussoirs. As they are laid side by side, gravity's relentless pull doesn't weaken the structure, it strengthens it. The weight of each stone pushes it against its neighbors, generating immense internal pressure, a force we call compression. This powerful force is channeled outwards and downwards, flowing seamlessly along the curve of the arch and into the sturdy piers that anchor it to the earth. The entire structure is held together by this constant, powerful squeeze. But constructing such a marvel was a monumental task in itself. First, a massive wooden support structure, a scaffold called centering, was painstakingly erected, perfectly mirroring the arch's intended curve. Upon this temporary framework, Roman workers, using cranes powered by human treadmills, meticulously hoisted and placed each voussoir. The tension on the worksite must have been palpable as they neared the apex. And then, the final magical piece, the keystone. As this central wedge-shaped stone was hammered firmly into place at the very crown of the arch, it locked the entire assembly together. The incredible compressive forces were now perfectly distributed. The moment of truth arrived. The wooden centering could be dismantled and removed, and, miraculously, the heavy stone arch stood firm on its own, a perfect testament to engineering, defying gravity itself. This foundational technology wasn't just for crossing rivers. The arch became the structural backbone of Roman civilization itself, from the soaring aqueducts that were the lifeblood of their cities, to the monumental arches of triumph and the enduring skeleton of the Colosseum. Each arch was a symphony of precision, a puzzle of physics solved with simple tools and profound ingenuity, allowing the arteries of the empire, its roads, its armies, and its water to flow uninterrupted across any terrain imaginable. After its long journey, the aqueduct's water didn't just spill into the streets. It arrived at a critical junction, a masterwork of hydraulic engineering known as the Castellum A, or water castle. This was the city's main distribution tank, the heart of the entire water system. Imagine a large, often ornate, covered basin. Water from the aqueduct poured into one side, its momentum slowed. This pause was deliberate. It allowed heavy sediment, sand, and grit to settle at the bottom, a simple but effective form of purification. Cleaner water from the top then flowed towards a series of outlets. These outlets were strategically placed at different heights. The system was designed with a brilliant civic hierarchy in mind. The lowest pipes, which received water first and longest, always supplied the public fountains. Water was a right for all citizens. The next set of pipes, placed slightly higher, channeled water to the public baths, a cornerstone of Roman social life. Only the highest pipes, the first to run dry in a shortage, supplied private villas for the wealthy who paid a special water tax. Each connection was made with a standardized lead pipe, or fistula, its diameter precisely regulated by law. The size of the pipe determined the flow, and thus the price. This wasn't just plumbing, it was a sophisticated system of resource management, ensuring that the city's essential needs were met before private luxury. A true testament to Roman practicality and public planning. But the aqueducts were far more than just engineering marvels. They were the very lifeblood of Rome, a constant, flowing pulse that transformed the city from a simple settlement into a thriving metropolis. Before their construction, Rome, like any ancient city, depended on the Tiber River and local springs. But with this new, endless supply of clean water, a revolution in urban living began. First came the fountains, the nasoni, dotting the city's corners. These weren't mere decorations, they were public utilities, providing fresh drinking water for everyone, rich or poor. Imagine the relief on a scorching summer day to have cool, clean water always within reach. Then came the magnificent public baths, the thermae. These were colossal complexes, not just for hygiene, but social hubs. Places to meet, exercise, and conduct business, all powered by the aqueduct's ceaseless flow. The scale was immense. The baths of Diocletian could hold thousands at once. Perhaps the most profound impact was on public health. The constant supply of water flushed the city's sewers, most famously the Cloaca Maxima. This sanitation system, revolutionary for its time, dramatically reduced disease and filth, making Rome a far healthier place to live than any other city of its era. This water didn't just serve the public. Wealthy patricians paid for private connections, bringing the luxury of running water directly into their villas, a symbol of ultimate status. Even industry benefited. Water-powered mills for grinding grain, feeding the city's massive population. In essence, the aqueducts were the engine of Roman daily life, underpinning its health, its social structure, and its very ability to grow. They made the monumental city of 1 million people possible. Rome's true foundation wasn't marble, but moving water. A city of 1 million people demanded a river, and the Romans built one in the sky. For centuries, a breathtaking network of 11 massive aqueducts snaked across the landscape, monumental arteries of stone and mortar. They carried a torrent of fresh, clean water from hills miles away, a constant life-giving pulse into the heart of the empire. This water was the engine of Roman daily life. It filled the colossal public baths, powered the ornate fountains that decorated every square, and, crucially, flushed the city's waste away through the great sewers, keeping disease at bay. It was a symphony of engineering, a testament to a power that could command nature itself. But what builds an empire can also break it. This vital system, so visible and sprawling, was a fragile lifeline. When the Ostrogoths, under their king Vitiges, laid siege to the city in 537 AD, they understood this vulnerability. They knew that a direct assault on the mighty Aurelian walls was a fool's errand. So, they waged a different kind of war. They targeted the aqueducts. With brutal efficiency, their warriors swarmed the countryside, not with siege towers, but with simple tools of destruction. The resonant thud of axes echoed as they hacked at the stone pillars. Fires were set against the foundations. Arches, which had stood for generations, were systematically broken. On the map, the glowing blue lines representing the aqueducts began to flicker and die, one by one. The torrent that supplied Rome slowed to a pitiful trickle, and then silence. The great fountains sputtered and went dry. The opulent baths became hollow, echoing chambers. Without the flushing power of the aqueducts, the Cloaca Maxima, the city's grand sewer, became a clogged vessel of pestilence. Disease, the unseen enemy, crept through the choked streets. Thirst and sickness did what armies could not. The population, once a teeming million, collapsed in a terrifyingly short span. The city bled out its people, shrinking to a mere ghost of its former self. A small town of perhaps 30,000 survivors rattling within the shell of a dead metropolis. The arteries had been severed, and Rome, the heart of the world, was finally, irrevocably dying.